Hello, it's great to have you back. This is week 6, and the topic of this week is partial differential equations in image processing. Some of you might remember, some of you might know what partial differential equations are, some of you might not remember when you studied that maybe a long time ago, maybe just a few years ago, but don't worry, as every other week, this is going to be a very self-contained week. Before I give you a bit more of details about what we are going to learn this week, let me try to explain to you what do we mean by partial differential equations. What is kind of this new area, relatively new area in image processing, but certainly new for us in this class. So far, we have been considering images as discrete objects in the computer. If we look, for example, at the still image, we already talked, it looks continuous to us, but actually it's a collection of pixels. So it's a discrete two-dimensional array of pixels as we have represented here. Now they are so close to each other, we already talked about resolution, they're so close to each other that it looks like a continuous image. But actually it is a discrete object. It's represented in the computer as a discrete object. The same happened with movies. We already know that movies are discrete objects. They look continuous to us, like this movie that we are watching here, because the sampling in time is basically very fast. And that's why our perception perceives this as a continuous object. But we already know that this is a discrete object, 30 frames per second, 24 frames per second. So images and videos are discrete both in space, in time, and also at the gray levels. They look continuous to us, but they're discrete objects. Now that leads us to what we have been doing most of these 5 previous weeks, using tools from discrete representations, from discrete mathematics, because we have discrete objects in the computer. So what's different when we start talking about partial differential equations? What's different is that we're going to start considering continuous objects. So when we consider discrete objects, the way images and videos are represented in the computer, we see, for example, sums. We never saw the sign of an integral. We always talk about sums. We talk about discrete operations. Also, every time we saw kind of a continuous object, a derivative, which is a tool from calculus, is a continuous object, then we immediately discretize it. Remember, we talk about, for example, x derivative in the x direction, and we say, okay, let's do plus 1 and minus 1 here. So immediately we redefine its discrete counterpart, because we want to be in discrete world, we want to be in a discrete space. The area of partial differential equations says, forget about that. The area of partial differential equations has a completely different approach and says, images are continuous objects. Don't treat them as discrete objects anymore. That's just an artifact of computer representations. Treat them as continuous objects. And then you basically are going to be talking about image processing as iterations of infinitesimal operators. Things that happen at very, very small scale. We iterate them, and when we are iterating them, actually we get these partial differential equations. That once again, if you don't remember exactly what they are, we're going to explain that in the next videos. Don't worry about that. The key concept is here. Images are not discrete objects, images are continuous. So go and develop all your algorithms like you're in continuous domain. Treat images as continuous objects. And then you can do partial differential equations. You can do also differential geometry. Tools that are from continuous mathematics, all of a sudden, they are valid, they are powerful for basically discrete image processing. But then you ask yourself, wait a second, you develop them, but my images are still discrete objects in my computer. But here comes to the rescue numerical analysis. Numerical analysis is exactly the area that says, how do I implement continuous algorithms? How do I implement continuous mathematics in discrete domains like a computer? So you go and develop algorithms with tools of continuous mathematics, and then numerical analysis comes to the rescue once we need to implement those algorithms in the computer. So it's kind of a different paradigm. It's not better, it's not worse. It's different than the paradigm that we were used to before, when we consider images from the very beginning as discrete objects. Now, why? Why is this happening now? What's going on? Why do we move from this completely discrete that basically, if we look historically, has mostly dominated image and video processing for years and years until basically about 10 years ago? And of course, there are a number of reasons why these continuous tools appear in image processing. One is computers became more powerful, and then numerical algorithms to implement this continuous math that were impossible to have in a computer became actually doable in even small and personal computers. Of course, every new tools come because some people move into the area, and we should never forget about the influence of people. So a lot of people in the last 10 years or so that were interested in continuous mathematics also became interested in image processing, and they brought their tools, their expertise into image processing. Now, we're going to see, as I said, we're going to see examples. I'm going to provide you the background. But why is it bringing to us? It's going to bring a number of things. It brings new concepts. It brings accuracy. This is a very important thing because we are in continuous domain, and then we implement by numerical algorithms. The accuracy will depend on the implementation, not on the design of the algorithm. The algorithm is designed in the continuous domain, so there is no intrinsic accuracy. Depending how much I'm willing to invest computational resources, for example, in the implementation, that will determine the actual accuracy of the algorithm. It's not intrinsic to the algorithm. When I define a derivative as plus minus plus 1 minus 1, I'm done. I have defined the accuracy of my algorithm. Now, if I define in the continuous domain and then say, do the derivative the best you can, I leave the door open to very high accuracy techniques. Another thing that was brought that we are not going to discuss a lot in this class, and certainly not in this week, is very formal analysis. A lot of the techniques that came from the area of partial differential equations to image processing have very formal analysis. You can prove theorems, you can prove that what you're doing is right, even before you're going and implementing the algorithm. So it's one of the most mathematical areas in image and video processing. I'm not saying it's the only one, but it's one of the most mathematical areas. And the consequences of this is that partial differential equation tools brought a lot of state-of-the-art algorithms. But I think one of the most important things, and I want to leave you before we go into details with this take-home message, is that there are new tools and new books in the bookshelf. So when you bring a new theory into an area, you say, okay, all these new frameworks are now allowed. And it's always good to have more tools to solve real problems, as we are going to see during this week and a bit next week. So what we're going to do this week is I'm going to give you the tools to understand the underlying and the simplest possible tools to understand the area of partial differential equations in image processing. We're going to filter in examples that is going to show you to understand. Remember, last week we discussed active contours. That's one example of the use of partial differential equations in image processing, as we are going to see very soon in one of the future videos. And we're also going to talk next week about image in painting, and some of the algorithms we are going to describe there are based on partial differential equations. As I said, it's one of the most mathematical areas that we are going to discuss during these 9 weeks of classes in image and video processing, but there's nothing to worry because I'm going to introduce you to the basic concepts and the basic tools that you need to understand the fundamental concepts behind this area of partial differential equations in image processing. And we're going to start learning about those concepts right in the next video. Thank you.